Good day everyone, my name is Levente Filip, I am from the University of Debrecen, Hungary, and today I will be speaking about benchmarking swarm intelligence algorithm regarding energy-aware clustering in wireless sensor networks using multiple metrics. Firstly, about the wireless sensor networks, these are a distributed collection of cheap sensor nodes deployed for real-time monitoring, often in remote or hard-to-access locations. Usually these are equipped with a limited energy supply such as a battery, therefore the challenge is to optimize their energy consumption so that the network can operate for a very long time. In case of a sensor node, the main energy consumption is the operation of the transmission circuit for the data transmission. This energy consumption is proportional with the distance the sensor node is transmitting to. Meaning the further it wants to transmit, the more energy it requires to operate the amplifier of this transmission circuit. In large-scale networks, some form of clusterization is used. This means we break up the sensor network into smaller clusters, and in each cluster we designate a sensor node to act as the cluster head. This cluster heads collects data, aggregates it, and transmits it with one transmission to the sink, or in other words, the base station. Here the cluster head's power consumption is higher than normal, but the other nodes in the cluster consume less energy because they have to transmit the data to much smaller distances. So overall, the energy usage of the sensor network is significantly decreased. However, to balance the workload of the cluster heads, these are rotated among the cluster nodes. There are many clustering models in the literature, the oldest one being the Leach model, which uses 5% of the total nodes to serve as cluster heads and rotating the cluster head roll randomly between them. However, several studies demonstrated that this model in combination with other optimization methods work even better. The challenge still is to determine which nodes to serve as cluster heads during the different episodes of a sensor network's lifespan. Such a decision, of course, is still an optimization problem. Also briefly about swarm intelligence algorithms. These are a class of meta-heuristic algorithms that use some nature-inspired search strategy. The swarm is usually composed of simple agents following very simple rules, but their collective collaboration looks like an intelligent behavior. These algorithms are quite good in optimization problems. How they work, each agent's position in the search space represents a candidate solution, and the quality of this candidate solution each is evaluated using a so-called fitness function. Back to our cluster head selection problem, we can define this with the following fitness function, where D1 is the maximum sensor cluster head distance. And we want to minimize this as we do not want clusters with very big distances in it. We also want to minimize the maximum cluster head base station distance, as we do not want clusters very far from the base station, as this will deplete the cluster head's energy reserves very quickly. And we also want to minimize the total energy consumption in any given VSN episode. These three values are weighted, and the objective of the swarm intelligence algorithm is to minimize the value of this function. We must also point out that the cluster head selection problem is a discrete optimization problem. Namely, we select the discrete nodes to act as the cluster head, but as in the literature, this problem is treated as a continuous optimization problem, as the majority of the swarm intelligence algorithms are continuous. This means that the objective space will have plateaus at the discrete values, meaning that in very short distances it will lag the slopes to guide the agents toward the optima. and we expect that this will impact the performance of these swarm intelligence algorithms we benchmark here. For testing, we have generated the layout of several sensor networks by placing the nodes on a random angle and a random radial length. Both of these can be concentrated or uniform. The four combination of these will result in four topologies, T1, T2, T3 and T4. On each topology we have generated four scenarios with 50, 100, 150 and 200 sensor nodes. For benchmarking we have used 10 swarm intelligence algorithm clustering with 5% cluster heads, but a minimum of 4. Swarm intelligence population of 20, iteration of 250, and we have ran each test 25 times. As for the results, first let's take a look at the raw performance, meaning the best score from the 25 runs. Using this we can beautifully rank these algorithms, and we can see that the PSO, despite being the oldest one, is the best performing here. We can also note that the node distribution, in other words the network's layout, affects the algorithm's performance. We can also note that in most scenarios the difference between the top performing algorithms was under 10% threshold values, so we consider these ones to perform very similarly. Next, we have considered the result variability, which is a generally underrated metric in the literature. This value is usually just presented as is without analyzed or interpreted. We especially focused on the outliers in the obtained results, which in our opinion is important, because if the best result of an algorithm is an outlier, it will not likely produce this result within a small number of runs. A quick explanation here: when we benchmark algorithms we tend to run them many times, but in real life we only run them a few times, especially when the fitness function evaluation is very costly. So the huge runs in benchmarks result can be deceptive compared to real life performance. So let's take a look at one of these results as an example of what we mean. On the T2 topology with 50 nodes, we seen that MVO was the best performing algorithm. But if we take a look at the result variability, we notice that this best result is just an outlier. The same is with the second best one, the CSO algorithm. If we remove these outliers, then they are not even the best algorithms anymore, but GTO is. Due to the landscape, we expected an impact on the performance of these algorithms, and we've seen exactly this, as many algorithms have their best scores as outliers. For the final metric, we take a look at the execution timing, which is very tricky to correctly measure on modern hardware, especially due to the turbo boost feature modern CPUs have, which must be disabled and the CPU to be locked at a constant frequency. As we see, with the increase of the number of sensor nodes, almost all algorithm execution time is increasing in a linear manner, meaning we can make good enough predictions how they will perform. And some conclusions briefly: we note the performance of these algorithms are influenced by the layout of the sensor network. We've seen that benchmarking and only considering the raw performance is insufficient for an accurate performance evaluation. Considering variability is good, but not enough. We recommend outlier analysis to be performed in such cases. We also seen the impact of the plateaus in the objective space. In other words, treating discrete optimization problem as continuous greatly reduces the performance of these algorithms. This is indicated by the many outliers in the results. Overall, we see that benchmarking and evaluating swarm intelligence algorithms is not as straightforward. Thank you for your attention.